Okay, so in Unit 2, we're actually going to look at a lot of the same things, a lot of the same kinds of motion, but from a different perspective. Okay? In Unit 1, we looked at something traveling at a constant velocity in terms of its displacement, its velocity, okay, the time. We looked at something that was accelerating from the standpoint of, again, what was its displacement, what was its change in velocity. In this unit, we'll still look at those things, but now we're going to look at what are the forces acting on them that are causing them to do that. Okay? So we're going to look at the simplest of Newton's first law, or Newton's laws today, Newton's first law. Okay? Now, Newton's first law, while part of rocket science, is not rocket science. Newton's first law says that if I don't do anything to this chair, it'll stay right there. Duh, of course it's going to stay right there. Okay? What is there not happening to it?
Nothing.
Nothing. Nothing's happening to it. I'm not pushing it. Now, does that mean there aren't any forces acting on it? What force is acting on it right now? Okay, is that the only force acting on it? No. There isn't. There is gravity, but there's another force as well. What's keeping it from falling? Floor. Okay? This goes to Newton's third law. Every action has an equal and opposite reaction. Okay? It's like the most often misapplied and misquoted of all physical laws. Okay? Gravity pulls this chair down into the floor. And the floor pushes back in the opposite direction with an equal amount of force, meaning those two forces cancel each other out. So the net force, the overall force on this chair right now is 0. There's no net force, right? You guys know what I mean by gross and net, right? If you have a part-time job, right, you get your paycheck and there's this really nice number, the gross pay, and then there's all the government extortion, right? Taxes, CDP, EI, all that stuff that comes off, union dues and all that kind of stuff. Okay, that all comes off, and then there's that sad number that says your net pay. That is after all the things have been accounted for. Well, when we're talking about forces, the net force is the vector sum of all the forces. So yeah, we're still going to be doing vector stuff in this unit. Okay? In this situation here, there's a force directly downwards, the weight of the chair, gravity, okay, and a force directly upwards, which we call the normal force. That is the reactive force of the floor. Okay? The chair is pushed into the floor floor reacts and pushes up with the same amount of force, the chair doesn't go anywhere. Okay? So, is there a situation where that that chair could move and also have no net force? If I put it on an incline, would it move at a constant velocity or would it accelerate? It would accelerate. So Newton's first law applies to situations where the net force is 0, or there's no net force at all. Under those situations, if there's no net force, there will be no change in velocity. So believe it or not, okay, that means that an object can move and have no net force acting on it. But it's only going to move at a constant velocity. Okay? Newton's law says if there's a net force, velocity will change. Okay? That means something could travel at a constant velocity and have no unbalanced forces acting on it. Okay? Everybody with me there? So, how many people have ever used the cruise control on their car? Okay. Your cruise control is trying to make sure all the forces acting on your car are balanced and keeps it moving at constant velocity. Okay? So if you set your cruise control and you're going up a hill, right, what does your engine do? Yeah, it works harder. It doesn't speed up, but it works harder, right? It generates more power, more forward force to overcome the downward force of gravity acting down the hill. And so your car works harder. It exerts more force up the hill because there's more force down the hill. right? If you're going down a hill, well, the engine might kick off completely. Okay, if you drive a hybrid vehicle, and like in my vehicle, if I'm going down a hill, it actually will start applying the brakes to keep me from going faster than the cruise that I've set it at. Okay, it makes sure that the net force is 0 and my car stays at the constant velocity. Okay. This can be a problem. Newton's first law can be a problem if you're in space. There isn't any force, right? There's no, like, if I'm out there and I don't have like a, maneuvering jets or anything like that, how do I get moving? I don't. I can flail around like a crazy person and it won't do anything at all. Okay? I mean, think about it. Even if you're falling and you flail, does it really do anything? And you've got air to push on in that situation. Okay? But if you're out in space, in the complete vacuum of space, flailing your arms around just makes you look scared, which you probably are. Okay? But it can't do anything to change your velocity because you can't push on. You can't exert a force. Okay? There's nothing to push on. That sort of makes sense? Now, this idea of Newton's first law can be summed up in one word. Okay? We call that word inertia. Okay? Newton's first law describes the inertia of an object. What kind of things do you think could affect your inertia? The other mass. Okay? Why did I make that distinction? There's a difference. Your weight is a force. Your weight is the force of gravity pulling your mass down. Your weight isn't measured in kilograms like your scale tells you. Okay? I don't know what your scale says when you step on it. Okay? I know what mine says. Get off! Get off! Doesn't like me very much. Okay? But okay, it tells me something in pounds or kilograms. That's not my weight. It's done the calculation. When I step on it, it feels my weight. Okay? It feels the force of gravity pulling down on me, and that compresses the spring that's inside, and it goes, oh God, you're so heavy. Okay? And the spring gets pushed in, and then it finally tells me, okay, given the amount of force you're exerting on me, and the fact that you're on Earth, you must have this much mass, and it tells me that mass. Okay? That number that's on your scale is not your weight. It is your mass. Okay? That is how much of you there is. Okay? So your mass can affect how much inertia you have. Okay? The bigger something is, the greater its tendency to keep doing what it's already doing. Okay? That's inertia. Okay? It's hard to change the inertia of something really big. Okay? Like for example, if I walk up to my chair here and I give it a little push, it moves. If I walk up to a train, okay, that's sitting on the tracks and I do that, the result is going to be a lot different. Okay? That train has way more mass, and as a result, it has way more inertia than my chair. Okay? I can change the inertia of the chair. Okay? I can change what it's doing easily. It doesn't have the ability to resist me very much, but something more massive does. Okay? I mean, think about this. How many skinny sumo wrestlers have you ever seen? They don't do very well. Sumo wrestling is all about pushing other people around. And the bigger you are, the harder you are to push around. That's why all sumo wrestlers are really big guys. Okay? It's why you don't see skinny linemen, okay, in football. Okay? They're too easy to push around. You need to be bigger. The more mass you have, the more inertia you have, the harder it will be to move you. Okay? It's just kind of common sense. Right? The bigger something is, the harder it's going to be to move. Making sense? All right. So any changes in inertia require a force. Newton's first law deals with only situations that involve no unbalanced forces. There are forces, but they're all balanced. They all add up to 0. Okay. So we got to define what a force is. Okay? A force is a push or a pull. Okay? Anything that acts on something else, okay, and can push it or pull it is a force. Okay? So gravity exerts a pull. Okay? As we'll learn in Unit 3, gravity is the mutual attractive force between two masses. Okay? So believe it or not, you're attracted to the Earth, and it's attracted to you in exactly the same way. The Earth is just as attracted to you as you are to it. Okay? So gravity is a pull. If I push on something, just applying it like directly an applied force, okay, that would be a push. Right? What would friction be? Yeah, it's a binding. Would it be a pull or a push? It can actually be both. Okay? It can be drag, but it can also be what gets you going. Would it be possible for me to walk right now, doing what I'm doing, if the floor beneath me was frictionless? I mean, we've all seen what people who've never experienced winter look like, right? It's kind of funny when they first experience winter, right? They go outside, they try to walk, boom, down they go like Bambi, okay? And they can't, because they don't understand it. When you walk on something very slippery with very little friction, you don't try to push against it. You pick up your foot, lean forward, set it down, and then move your weight to that foot. Like, we don't know how to walk on it. Like, be careful, okay? And we don't push very much because we understand it. Half of our lives have been spent in the winter. Right? But if you don't know that and you try to push, there's no friction to push back. Okay? In a Newton's third law kind of a situation. Okay? I exert a force, okay, that way, and the floor pushes me this way. Without friction, I have no way. So friction can be a push or a pull. Okay? Some forces work. Okay, so these would be some examples here. Okay, obviously if gravity is acting on this baseball, gravity is what causes it to fly in that projectile arc that we talked about. Like, a bunch of the Jays did last night. Okay. I mean, this whole World Series has been like dinger after dinger. Like, holy smoke, it's like a home run derby. Okay, everybody's just hitting it out of the park, it seems. What about this force right here? Okay, the one that's let's say that this truck is traveling at a constant velocity. What's the net force acting on the car? If the truck's traveling at a constant velocity, is the car traveling at a constant velocity? Yes. Okay. So what's the net force? Zero. Okay. The net force in that situation would be zero. The truck pulls this way through the cable on the car. So the forces the car is experiencing are gravity, a forward force, and friction. Okay? And then the upward component of this force. Okay? So there would be force of friction, there would be the forward or horizontal component of this force. Okay, so force horizontal, and there would be this force vertical, the vertical component of that angled force, and gravity. Well, this force and this force are the same size, so they cancel. Friction and the horizontal component of the cable are the same size, so they cancel. So the car moves at a constant velocity. There's no net force. Now, what if the truck accelerates? Well, the car will have to accelerate as well because it's attached, right? But what will change, okay, is now this horizontal part of that force will get larger, because if the truck starts to accelerate, you're right, initially the car falls behind. This angle will change, right? And it'll change because that forward part gets a little bigger. Now there is a net force. Now what does the car do? Now it speeds up. Now there is a net force. The forces are balanced. Okay? So all of the stuff we see, and this is where, like, this is kind of the unit where you'll start to view the world a little differently, in a good way. Okay? You'll start to see how things work, okay, in terms of pushes and pulls and things like that. Okay? You'll see the world like I do. Like, oh man, there's this really heavy thing in the back of my truck, or I need to get this really heavy thing in the back of my truck. I can't lift it. Well, I'll build a ramp, and then when I'm building this, everyone would build a ramp, right? That's common sense. But when I build a ramp, I'm like, okay, it needs to be this long so that I only have to work against this much of gravity. Like you'll start to see the arrows that I'm drawing here, you'll start to see those, okay? That's all part of this unit, is being able to identify those forces. How are they big? How are they small? How do they relate to each other? What direction are they going? Okay? And it gives you a better understanding of how can I make something happen for myself, okay? All right, so force is a vector quantity. It has magnitude and direction. Okay? That's why your weight is a force, right? It's directed downwards. It's gravity pulling you, your mass, towards the center of the earth. Okay? That's why when you step on the scale, you'll compress the spring. Okay, so mass and weight, two different things. Weight's a force. It's the force of gravity pulling on your mass. Mass is simply how much of you there is. Okay? But in North America, we mess this up all the time. Okay? I got to get in the gym. I got to put on some weight. Well, yeah, if you go to the gym and you do exercises that are going to build muscle, yes, your weight is going to increase. But only because your mass is increasing. You're putting on muscle mass, right? You are, well, making more of you. Okay, if you go to work out, okay, to get more muscle, you're going to put on mass. There will be more of you. Okay, if you go to the gym to lose weight, okay, then you're trying to burn calories and make less of you. You'll have less mass. Okay, if I want to lose weight, I just go to the moon. Okay, I'll weigh 1/6 of what I do here. There won't be any less of me. Okay, there'll just be less gravity. I'll weigh less. Yay. Okay. Way to beat the system if you can get to the moon. Okay, but I mean, even if I went to a higher altitude, I would weigh less. Okay, the further from the center of the earth you get, the less you will weigh. Okay, actually exponentially so. Right, so mass, very simply, mass is how much matter makes up an object. So a penny, not very much mass, because there's not very much matter. Okay, a supertanker, a lot of mass. Okay, because there's a lot of matter. Okay, I mean, it comes right down to it. Two objects are coming towards you in the street. You don't have time to get out of both of their ways. One of them is a child on a tricycle. The other is a bus. And they are both moving at, let's say, 10 kilometers an hour. That's really fast for a kid on a bike, but let's just say, okay? One of them's going to hit me. Provided I want to live, okay, I'm probably going to want to step in front of the kid. I have a better chance of stopping him because he has less inertia and less mass. Okay, if I step in front of the bus, okay, I'm not Superman. I'm not just going to put my shoulder down and have the bus flip over me. Okay, I mean, that'd be cool, but it's not going to work. Okay. Yeah, for breaking all the laws of physics. Unless Superman is incredibly massive, all of that stuff just doesn't work. Okay? Don't overthink it, it'll really ruin all superheroes for you. Okay? Okay. Mass is a scalar quantity. Your mass doesn't have direction. It's how much of you there is. Nobody says, I'm, 72 kilograms north. I mean, south maybe, when you're putting on weight, but it doesn't have a direction, okay? It's just how much matter you possess. So mass is a scalar quantity where weight is a vector. Okay, so weight and mass, two different things. They're related to each other, okay? Mass influences weight, okay, but they are different. Okay, so weight is the force of gravity acting on your mass. So when you go to the gym, you go, I gotta go lift weights. You're really going and lifting masses. Okay? You're working against their weight, but you are lifting masses. Don't say it like that, or some big roid monkey will beat the hell out of you. Sounding weird. Okay? I don't know. I don't go to the gym anymore. The roid monkeys scare me. They're always very angry. Very angry. Okay. Don't take their weights either. Okay? They get really angry if you take their weights. Like, they'll chase you with them. That's never happened. Okay. Just be fast. Okay. Now, Newton's first law, okay, kind of a simple way to kind of illustrate that is if you're like winding up for a slap shot like this guy, okay? Now, let's say it's that the puck is moving towards you. The ice is completely frictionless. Okay, so this is like Leon setting up for a one-timer from Connor. Okay, so the puck is sliding along the ice. The ice is frictionless, so the puck is traveling at a constant velocity. Okay, what causes the puck to move towards the goal? Well, actually, the force you exert on the stick. And now, if the stick is heavy, then it has more inertia, right? And it can cause bigger changes, right? It's why there are kind of regulations on how big a stick can be. Okay? It's why there's regulations in baseball about how big or heavy the bat can be, right? One of the most common forms of cheating in baseball, besides steroids, okay, is corking a bat, which means to basically drill it out and fill it with cork. Now it's lighter. Can you swing it faster? Okay, lighter bat, okay, less inertia, I can make it go faster. The faster I can swing it, the further I can hit a ball when I make contact, provided I haven't taken too much of the structural integrity of the bat away. Okay, there's a possibility that I could destroy the bat, okay, because now it has less mass, right? Okay, so puck is moving towards this person, okay? The net force on the puck is 0. When he makes contact with the puck, the net force will no longer be 0. Okay? It'll be some number of newtons. Incidentally, newtons are the units for force. Okay? And that will be directed, hopefully, towards the goal. Okay? Will that result in a change in velocity of the puck? It'll accelerate, right? Accelerations require net force. Whatever direction that net force is, that's the direction the object will accelerate. That's Newton's second law. It's actually what we spend much of the unit talking about. Okay? If that guy swings and misses, what will the puck do? Yeah, in a straight line. Okay? This is kind of how curling works. Okay? If you just slide the rock and you don't put any spin on it, the rock will go perfectly straight. Okay? If that ice is totally frictionless, it would never change speed. Okay? If you had like an infinitely long sheet of curling ice, okay, the rock, once you push it, will go forever. Okay? Because there's nothing to stop it. If the net force is 0, there's nothing to slow it down, there's nothing to speed it up. It would go forever. That's where astronauts have to be careful. If you're out in space and you get moving, and you have no way to exert any force, you will float away. Is that bad news? It's really bad news if you're that astronaut. There's a long way to float. Okay, you're gonna run out of oxygen. Okay, all of that kind of would be scary. Okay? That's why they very rarely do any EVAs, so extravehicular activities, without a tether. Okay? If you've seen The Martian, okay, near the end, they had the one guy outside of the spacecraft, and he was moving along the spacecraft, kind of like throwing himself along, okay, without a tether. That's really dangerous. All that has to happen is you don't push quite right, okay, or the spacecraft moves a little bit, you fly off, and you're flying off, you're going straight, and this thing is going that way, and you've got nothing you can do to stop. Okay, it was also a big problem when they were trying to catch Mark Watney. Okay, they're like, well, I'll just wave to you as you go by because he was out of fuel. Okay, what did he do? Anyone remember? He needed to get moving, he needed to change his velocity, he needed to accelerate, so he punctured his glove. Right? You puncture your spacesuit in space, what comes out? Air. All the air. Okay? Can I push? He said, I'm going to be like Iron Man, right? So he was just going to, I don't know if you know superheroes, but he can do this with his hands, and that's like thrusters. Okay? So what he did is he just pointed the escaping gases in the opposite direction he wanted to go, okay? And he was able to maneuver himself. When he first did it, and there was so much pressure, he like flew off in the wrong direction. He had to make correction changes. Okay? Now, there is a downside to that. Once you puncture the suit, eventually you're going to run out of what? Air. That'll be bad for you. Pressure and oxygen are all kind of important for you. So he would like close his hand and then he would open it again. But if you can't do that, or once you run out, whatever direction you were going in at that time is the direction you are going to have forever. And you will simply drift away. All right, I'm going to show you a little video to do with that. Okay, so, I mean, we give the smart car a hard time because it's small and doesn't have a lot of mass. A smart car is also not designed to be driven at highway speeds. Okay, those two cars that we saw, they're designed for stop and go traffic, maybe 80 kilometers per hour. Okay, but you know, you see people driving those little things down the Deerfoot at 125, 130. They've got to have them right to the floor. Okay, because they're not really designed to go very fast. Okay, they're not safe at that speed, but that's not what they were designed for either. Okay, they were designed to be efficient, stop and go traffic. Okay, so it's a bit of a, you know, an unfair test. Our purpose of watching that is to show, okay, what parts are important in a collision, why does mass matter, okay, how does mass affect inertia? That's what we were looking at. Okay, now, so Newton's first law says that an object at rest will remain at rest, and an object traveling at a constant, well, I should say velocity, okay, will continue to do so unless acted upon by a net force. So this should actually say velocity. Why am I making that distinction? There is a difference. One's scalar, one's vector. It's possible to accelerate while traveling at a constant speed. That's what you do when you turn. Okay? You take a turn, you could go 20 kilometers per hour through the whole turn. Your speed is constant. Is your velocity? You're turning. Your velocity is changing because your direction is changing. Okay? That's why it takes friction to help you turn. Okay? The guy that ended up in the pond there, okay, or the guy that took out the pole last year, okay, they didn't understand that you have to have a force that pushes you back towards the center of the turn in order to make the turn. If there's no force there, you will go in a straight line. Okay? You'll remember that the first time it gets icy and you're driving. Okay? You go to turn a corner and your car goes straight. Okay? It's simply obeying Newton's first law. It's going to continue to travel at a constant velocity because there's no net force to do anything else. So you just travel straight. Okay? We'll talk a bit more about that when we're in the circle unit. We'll make more fun of the people who end up in the pond or take out posts. It's physics. All right, so I would say definitely have that part that's in bold there, copy that down. That's Newton's first law. That's super important. Okay. Has anybody seen the magic trick where you pull the tablecloth out from underneath the dishes? Okay. Anyone ever tried it? Try it, but not with mom's best china. Okay, like go to the dollar store, get some plastic dishes. Get a dollar store plastic tablecloth. Don't use a cloth tablecloth. Okay, because we want something that's sticky or slippery. Yeah, you want something really slippery. So you want the ones that have that kind of plasticky vinyl covering on it. Okay, so it'll slide real easy. Now, what people do wrong with that trick is how they pull the tablecloth. Okay, so if I'm doing that trick and this desk is the table, okay, do I want to pull this way, upwards and away on the tablecloth, or do I want to push against the table and pull down? Which one? Down. I want that tablecloth to slide straight toward me. If I pull up, I'm going to lift the tablecloth. I'm going to lift up all the dishes, and they're going to go crashing away. Okay? If I want to do that correctly, I want to push the tablecloth against the edge of the table and down. Then it can only slide straight towards me. It will slide out from under the dishes because the inertia of the dishes is to stay put. They are currently at rest, and if there are no unbalanced forces, they'll remain at rest. Okay? If I do that really quickly, okay, it'll slip right out from underneath them. Now, which would make it easier? Heavy dishes or light dishes? Heavy. More mass, more inertia. More likely to stay put the heavier they are. Okay? Now, to an extent, you don't want to put a sidewalk block on top and try and pull it out from underneath. That's too much mass. That creates too much friction. Okay, there's a kind of a delicate point there where mass creates more friction. Okay. All right, so that's how that would work. Okay, there's all kinds of other situations, like if you made a stack of checkers or like poker chips or something like that. If you flick one at the bottom of the stack, okay, you should be able to knock the bottom one out, and the stack just falls straight back down and doesn't tip over. Okay, Jenga is similar. Like you gotta slowly pull out those blocks without changing the inertia and the balance of the rest of the tower. Okay, it's also, here's a thought, you can entertain yourself the next time you're in the bathroom. It's how toilet paper works. Okay, if you just want to rip off a single square from the roll, okay, can you do it without putting your hand on the roll? Can you just go like really quick and have it tear along the perforations? Try it. You absolutely can. Easier with a full roll or half or less roll? Full roll. More inertia. If the roll is brand new, there's more paper on it. It's heavier. It has less likelihood of moving. So if you grab one square and just do this, okay, it's likely it will tear along the perforation because the inertia of the rest of the roll is too big to unroll the whole thing. Try that with half a roll or less, do that, and you're going to have a whole bunch of toilet paper in a pile on the floor. Okay. If you need to be entertained in the bathroom, don't take your phone in there, okay, just try, play with the toilet paper, okay, and you'll see Newton's first law in action. Okay? It's weird how many things physics governs, even things like toilet paper. Okay? All right, now I think this is these guys doing the tablecloth trick with the Lamborghini, if I recall. So that's how it would work if we have no net force. Okay, the diagram in black here is showing a net force. Okay, so what we have is a book sitting on a tabletop. Let's just say it's the power cord thing. Okay. So if it's sitting on the tabletop and I push it this way, okay, I push with 20 newtons worth of force. What's the 18 newtons pushing the other way? Friction. Yeah, friction would be resisting it. Okay, but if I have 2 newtons more than friction, what does this thing do? It slides, but it also starts with A? Accelerates. There's a net force, right? The net force isn't zero. There's a situation where I can push this at a constant velocity. How hard am I pushing it? If there's 18 newtons worth of friction, and I push it so it moves at a constant velocity, I'm pushing with 18 newtons. The net force is 0, and it moves at a constant velocity. But if I push with more than 18 newtons, the object accelerates. Okay? But here's the kicker. That acceleration only occurs for as long as I'm what? As long as I'm pushing. Okay? So I give it that push, but as soon as I'm not pushing on it, it slows to a stop right away, because now instead of having a net force of 2 newtons that way, it has a net force of 18 newtons backwards. Okay? And it slows it to a stop. Any situation where the velocity changes is governed by Newton's second law. Okay? Everybody with me there? Okay? If there's an acceleration, that means there is an unbalanced or net force that's acting on the object. Okay, so we were talking about how mass is related to inertia. Okay, obviously a penny is a mass of about 3 grams, not that we even have those anymore. Okay, a book, a mass of about 2 kilograms. It would be much easier to move the penny than to move the book. Okay, a bicycle, 15 kilograms. Okay, obviously it's going to take more force to move the book. Okay, if you've ever had to push a stalled car, okay, you know you have to push pretty hard on those because they have more inertia. I don't think anyone's tried to push a stalled plane. Okay, but obviously that would be even harder because it's a lot heavier. Okay, pushing a super tanker would also be pretty hard because you have to be in water, and that would be problematic in and of itself. Okay, but more mass means more inertia. That's why we talk about why you don't see skinny sumo wrestlers. Okay. Okay, so the inertia of an object measured by its mass. So inertia is the natural tendency of an object Okay, to remain at rest or in motion at a, this should say again, velocity, constant velocity. Okay, along a straight line. That's the key. Remember, velocity is a vector quantity. If you turn, that's an acceleration. Changing direction still counts as an acceleration because it is changing the vector of the velocity. Okay, does that make sense? The good news about Newton's first law is there's no math. Okay, like there's no problem solving to do with Newton's first law. There's no forces. Well, there are forces, but there's no net force. The object is either traveling at a constant velocity or sitting still. Okay, there's not much to do with that other than to recognize that this is a situation governed by Newton's first law. Okay, we're going to talk about all the situations governed by Newton's second law starting tomorrow. Okay, if I don't have your vector assignment, I want it tomorrow at the absolute latest because I want to go over it starting class tomorrow. Okay, before I get into Newton's second law.
Good morning.
No quiz tomorrow.
Yes,
no quizzes probably for the rest. Okay.
In the name of the Father, and the Son, and the Holy Spirit.